Everybody, yep, just a quick reminder, there's a lot, we have a ton of free stuff. Please come and get it so we don't have to take it back with us to Chicago. In addition, we're going to be giving away a drone at the end of this. Just warning, if you win and you don't want to take a picture, you don't get the drone. There has to be a willingness to take a picture with Jason. But that'll happen tomorrow sometime, Daniel, is that right? Yeah. Yeah, we'll do it sometime tomorrow. Cool. So I'm here with Jason Kraft. He's a senior network engineer at Telnyx, and we're here to tell you a little bit about the network that we've built. So before we do that, I sort of want to frame it for you. And what it really comes down to is real-time communications over the internet is not yet a solved problem. I think some people might argue with me on this, and so I'm going to get very specific on what part of it is not solved. But ultimately, what we're seeing is a transition from device-centric communication to application-centric communication. There's only one fabric that's capable of facilitating application-centric communication. That fabric is the internet, and unfortunately, the internet wasn't designed for voice. So I'm going to go over this particular problem, and I'm sure many of you know what's happening with net neutrality, at least in the United States, with the FCC looking to reverse the changes to Title II, I think that's what it is, classifying ISPs as utilities. That's going away. But even as that was happening, there was a war going on between the eyeball networks and the content providers. And so I'm going to use the example of Comcast and Netflix, because I think that one has probably the most written up about it. So this is covered in the peering playbook by Bill Norton, is that right? He talks about sort of how Comcast forced Netflix to pay for peering. And so what Comcast did was oversubscribe their transit links. So they are tier one ISP, so they peer with all their tier one ISPs, but in the cases where they don't have direct peering, they buy transit. So what Comcast did was just ensure that the transit was oversubscribed during peak times. What that meant was that if you were sending anything down their transit links, you would have packet loss and overall, I mean, just throttling, and things would happen that you didn't want to happen. And what we're saying is when things like this happen, real-time communications, even though it's not necessarily intended, is often a casualty. So what we did was we took a different approach. We built a phone company with the internet in mind. And so the idea is, conventional wisdom was to build carrier-centric infrastructure. So you have the incumbent has an entire network that they've built over the last century. Why not use what they've built? And that made total sense when the last mile was a copper circuit running to a business or a home. But now the last mile is the internet. So instead of building into the carrier hotels, it makes more sense to build into the internet hubs. And so that's what we did. So the idea is buy access to these eyeball networks, whether it be by getting a voice interconnect or actually just buying transit, but in essence being one hop away from all potential subscribers. Then order cross connects to the cloud service providers so that you have access to infinitely or almost infinitely scalable technology, right? And more importantly, do it in a way in which you have multiple cloud service providers per geo. So again, the idea is, I think we're all aware that Amazon and others are not offering 5 nines. The expectation of a carrier-grade product is to deliver 5 nines. So how do you do it? And the answer is you cluster across multiple CSPs. And in doing so, you can deliver the SLA that customers have come to expect from a carrier. Then we connect the sites using MPLS-TE, so we can do things like RSVP, protect the packets from end to end. But the general idea is do the call processing locally, take the call off the internet, and then ride it on your own backbone until you can get it to its destination. So as you can see here, we're using our own IP address space. We have an ASN. But also, I sort of snuck it in here, you'll see that there's an OCN. So this is I'm not sure what the European equivalent is, though we are pursuing this strategy everywhere that we can. But in the United States, there was an order passed called 1570 that allowed IP-enabled or interconnected VoIP providers to get a designation called IPES, or IP-enabled service. And what this allows us to do is essentially put ourselves in the LURG, or the routing guide, and tell people, hey, we're an IPES, we have our own blocks, and instead of delivering those calls to us over the circuit switch network, you can deliver those calls to us over IP. So when the call is made to one of our numbers, the LRN points to Telnyx, and then if they have an agreement with Telnyx, they can send that call to us over IP. So I think that's pretty cool as well.
All right, so let's talk about our point of presence, as it were, and let's talk about why we have this to begin with. So, if you're out there, if a network is your desire to build, you need a place to actually do it, right? So you need a point of presence. For us, we decided early on that the intention was to get as close to the customers as possible. In other words, shorten the path. So the idea now is that these points of presence that we're going to talk about here are globally built. So we have many points of presence that are distributed across the globe. We started in the US and then expanded to Europe recently. And so the idea here is that we're talking about a small network footprint. So instead of building rows of cabinets, of servers, various types of infrastructure, a couple of things that we did was we decided we can do this with a small network footprint, and then also utilize the cloud as our data center. So let's talk a little bit about how we actually started with this. So this is the picture of our standard topology that you would see in a point of presence. And we start out with a couple of edge routers, a couple of core routers, and essentially this is forming the basic backbone at the local POP. So providing the ability for us to actually build out our environment. We then also have an ag router at the local site, and this is basically providing the routing between our backbone and the cloud providers. At each location, we have at least 2 transit peers that we connect to, and these are just basically allowing us to present our IP traffic to the outside world. Additionally, we're in every location that we're at, we participate in an internet exchange point, and this basically is a fabric at each facility that allows you to connect to other various participants, so like the Googles, Netflixes, other carriers, customer networks that are also on the same fabric. And this allows us to take that traffic off of transit and just peer directly over the IX. Additionally, what's not on here is direct connections. So direct connections are similar to IX, in which you can actually form a direct cross-connect with the people that you want to peer with. Also, at each location, we have our own backhaul, our own backbone. As David talked about earlier, our MPLS backbone. So this is something that we've built from site to site. And all of our various POPs are interconnected in this manner. And then lastly, we have our telephony engine, or what we call our tanker. So a tanker is what you'll hear about soon enough is a collection of containers that are hosting our telephony engine. And additionally, off of the ag router, we have our connections into the cloud service providers.
So this is the architecture. I didn't mean to overwhelm you, and we'll sort of go into detail, but the idea is it's multi-service-based, microservice-based. We use, let me just go through the components like this, so it'll be a little bit easier. An inbound proxy, this is Kamailio, sitting at the edge. It's pretty much what everyone interacts with before actually hitting the back-to-back user agents. The IBP talks to edge router. Edge router is a series of services that instruct the IBP in terms of where to send the call. So the idea is calls may come in to a given IBP on shortest AS path, but that may not necessarily be the lowest latency path. So in this particular case, if you have someone in between, let's call it Chicago and Ashburn, Tennessee, their shortest AS path might take them to Ashburn, but you have a lower latency connection to Chicago. We're going to anchor the media in Chicago on that particular back-to-back user agent. So that's essentially what the edge router does. Then we have the back-to-back user agent. Shout out to FreeSwitch. That's what we're using for transcoding and pretty much everything related to media. The back-to-back user agent talks to a dial plan service. So we use mod XML curl, I think I got that right, or mod curl XML, one or the other, to communicate with a web server that generates the dial plan. Again, a series of services that puts that together. When calls go off net, they leverage a routing engine. That routing engine finds the best off-net carrier to use the call with. So ideally, it goes over a direct connection, but if we don't have a direct to a given carrier, we'll just use LCR. And then last but not least, there's an outbound load balancer associated with that routing engine, and that's to enforce carrier rules around time of day, number of concurrent calls, CPS. And then we have the registry. So for customers that don't have fixed IP or FQDN, they can register with the registry, and in turn, we can deliver calls to them to the last registered point. So the idea is, this is a off-net termination call. Customer makes a call, signaling takes the call to IBP. IBP asks the edge router, hey, where do I put it? It sends it to the back-to-back user agent. Back-to-back user agent asks the dial plan, hey, how do I get the call to wherever it needs to go? It says, okay, this one's off-net. Let me take it to the routing engine. Routing engine then says, okay, this is going to Tata. Hits the OBLB, again, this is Kamailio, to make a determination whether or not we have capacity there. If we do, the call continues, otherwise we'll 503 and it'll go to the next destination. Orig, very similar. So either you're coming in via the Orig partner, so someone that has an IP interconnect with us, or if you're coming in over the circuit switch network, the access homing tandem provider that's taking that call off of the circuit switch network and giving it to us over IP, again, hits the IBP, asks the edge router, hey, where is this customer? Because we anchor the media always closest to the customer. Hey, the customer is in Chicago. Okay, well, we're gonna anchor the media in Chicago then. In turn, go out the IBP, and then hit the customer. Registration, this is pretty straightforward. Hits the IBP, we recognize it's a register request, and then we send it to the registry. WebRTC, same thing, gets a little fancier with stun and turn, but you get the gist. So the idea, again, from a multi-site perspective, just in case it wasn't clear, because we sort of used one telephony engine there, is user comes in to the site, the IBP determines, hey, actually this user is closer to site B, sends it to the back-to-back user agent in site B. That in turn goes to the routing engine. Similarly, into the IBP, out to the back-to-back user agent, IBP. Everybody get the gist? Nods, some nods, a little bit of nods. I'll let Jason go.
All right, so now we're going to talk about how we're, from a networking perspective, how we're deploying the telephony engine, or how we're making it available to our network and then thus out to the internet. All right, so this is the basic topology that we've deployed at all of our locations. So it's pretty much our ag router having a LAN subnet, LAN segment that interconnects the tankers that are home to the telephony engine. That segment has a basic IP subnet that allows reachability between the hosts, so the ag router and the two tankers. And then on the tanker itself, we actually build a routing process, and this process is what we'll see here in a second as what we're actually using to announce certain prefixes and certain IP address space into the backbone. So with Docker, what we're doing from our containerization perspective is we need access to the IP addresses on the containers themselves. So initially you turn up Docker, you want to run an application on it. Most people don't care about the addresses. They just load their app, start using it, everything's great. And in our world, we need to have access to the actual IPs of the containers because that's where the actual telephony engine is at. So we create custom Docker bridges to do that. Our containers then connect into the bridges. And then we're able to actually build subnets that are from our own private allocation from our backbone onto the Docker bridges to assign address space to the containers themselves. All right, so let's talk about that's all great, but we now need to get these subnets and IPs out to the backbone and to the world so that they can be reachable. So let's talk about what tanker router is. So tanker router is just nothing more than a term that we coined for running a routing process on the tanker instance. This router will actually form BGP sessions up to the local ag router at the POP, and then announce the bridges, announce the subnets, and then thus you have IP reachability. So let's see what that looks like in detail. So we have our topology. And so with running BGP, if anyone's familiar with it, you'll need an autonomous system number. And internally, we basically use a private ASN for all of our tankers. So our tankers become routing domains. They're essentially responsible for announcing their address space that they're hosting and also determining routing policies as needed. BGP sessions are formed with the AG router. And then the tankers announce the subnets that they are that we have configured on each instance. And once this is done, you have IP reachability between the containers. So the IBP, the B2B UA, they have actual IP addresses that are assigned by us. And then they have IP reachability. They can talk back and forth between each other, between other containers, or nodes upstream in the backbone. So that's great, but we still need to get it to the outside world. All of those IPs were private, and we don't really want to do NAT if we can avoid it. So what can we actually do to make these addresses available without adding more configuration overhead into the environment? We'll get to that. Yeah. So in order to accomplish this, we're going to zoom down in and take a look at the tanker. So this is a zoomed in view of one of the tankers from the earlier picture. And we're basically we're taking the same method from the tankers into the containers themselves. So we're basically installing a routing daemon on the container, running the application, and then forming BGP sessions locally within the tanker domain that we talked about earlier. So these containers are peered with the actual tanker. The tanker then is peered with the upstream AG router, and propagation happens in this manner. But now what we need to do is assign public IP addresses to the containers that we need to have reachable on the internet. So what we have now is we're adding IPs to the interfaces of the actual containers. So essentially that means when they receive a packet with that IP in the destination, they're going to listen and respond to it. The containers then announce those IPs as host routes in our network. So what'll happen is you'll see a host route floating around in the backbone for either the IBP or the B2B UA or any other parts of the infrastructure. And those host routes are then pinned essentially to these containers. So no matter where you actually target it from either the world or within our backbone, you'll route accordingly across the environment to the tanker and thus the container that announced the address space. So in summary, what we've actually built is we've built a distributed network where we can take the POP model that we talked about, the tanker router model, the container router model, and deploy this at essentially any location where it's deemed necessary to be. So in the past, you may have been coupled with, okay, we're going to build a POP and then a data center and then a lot of rows, a lot of cabinets, a lot of infrastructure, a lot of cost, a lot of hours, a lot of everything. And we basically put it into a model where we can have a small network footprint, use the cloud as the data center, use containers as a means to announce our telephony engine into the outside world, and then scale it and then build it quickly. So we can build a POP. If we decide in 30 days we need to be in said POP, we can go there, build this up in a day, automate everything from end to end, build the site, and have it essentially usable the day after. And so this allows us to, at this point in time, we're in 5 locations. We'll be in 7 by the end of June. And so we're able to then distribute and scale the infrastructure in a rapid way.
Yeah, any questions?
Yeah. Good.
So you mentioned you stuck to IP addresses on the Docker containers. And
right.
Why not to use, for example, a console or so and get to the DNS thing yet?
Yeah, so you can talk about any case. Because we're using, in this particular case, yeah, so sure, but in the example, if you go back to a couple here, you'll see that we're actually taking public IP address space and advertising it out. So you're using anycast all the way up. So in this particular case, if you have somebody that, I mean, you could use DNS, but if you have somebody that either, DNS has a whole range of issues around propagation and everything else. This gives you sort of the ability to instantly shift traffic around as necessary, right? Because you can remove a BGP advertisement from the internet relatively quickly. Well, you don't have to remove it from the internet. You just got to do it on your backbone, and then it'll route around.
So the other aspect of this model is, like, for example, this B2B container. If this is in San Jose today with this specific unicast address, we can essentially within minutes shut it down and move it over to another POP if necessary. And we've had use cases where that has come into play.
The IPs become global IPs.
Yeah. So rather than here's a server that's pinned to an IP address today, it's cabled up, it's boxed into this one location.
Containers can, for example, propagate their addresses to console, and console can do all this stuff for them.
Yeah, so we use console a lot, but we don't use it in the telephony engine. So I guess how would you? I'm curious. How would you propose getting the console to handle the public side of the transactions? Because we use it internally for microservices and identifying where to route a particular web call.
I know the console is widely used, for example, for services registered on a Docker container register on the console. And
That's right.
Can give DNS names, for example, and then use these DNS names for stuck to IP addresses.
Right. But ultimately, the problem that we're trying to solve is to get that container to be public, right? So you want to we're taking the traffic is routing over the public internet down to that container. You can't accomplish that with console.
If I understand
you can accomplish internal services and doing service discovery with console, but you can't tell the internet, hey, this particular container is sitting in Amazon East right now. Actually, no, it's sitting now in Azure East, right? That's just not possible via console today.
But you would still need to translate, right? I mean, so the IP. So ultimately, the.
But we can talk more. We can talk more about it. Yeah.
I'm curious about this because let's talk about it after.
I'm a bit sorry, but you have a problem with your slide. I don't find any current IP addresses on there. I just see the legacy IPv4 stuff we used years ago.
Yeah. So V6 is, and you might be able to speak to some of the limitations that we've seen, or at least, but V6 is something we have, and we just haven't actually built it within the telephony engine yet. So I believe we're still exploring that on our stack.
We're going to do V6 soon.
Yeah. It would make.
I'll remember that.
Yeah.
Next year.
No. You talked about using BGP to shift address space, but how granular is that? Because most service providers actually route filter prefixes.
Yeah, so the way that we handle routing with the internet is, so we have two major blocks of address space that we have currently, or however many we need, right? And those are the address blocks that the internet sees. So, and they're announced from every POP. So every single POP announces the same address space, gets into the globe,
right?
Yeah. So we have /19 of v4 address space where we use most of our IP allocation from. So that is what is seen in the global routing table. So from there, your service providers are going to take you to the closest network, or the Telnyx POP that it can find. Once it enters the Telnyx network at the edge, then our backbone is aware of all of the host routes that we're advertising across. So if you are ingressing into our London POP and you're destined for a San Jose container, the internet doesn't know about the actual host route, obviously, but then it'll hit the edge, go down into our core, and then our core knows how to actually find that address.
Yep.
Yeah, just a question. What do you use for orchestration of your Docker containers?
We use Ansible, and then we use Nomad
No more.
with console for service discovery.
Other questions?
Cool.
Okay, then thank you
Thanks,
very
everyone.
much, David, Jason.